shift the discussion slightly. There's a couple things I made some notes to pick up along the way. One of them is that Dan was mentioning that we saw PPG collectors replaced in a terrific rate, and we should cite that those were the original PPG flat plate collectors. Since then, there has been some improvement in their systems, and they have, for example, an evacuated tube collector that Louis Owings is producing that is showing much more promise. We saw that in the Louis Owings Forum at National Bureau of Science. We should say something about their mission. They are not doing any research in initiating systems. NBS their mission is to produce the standards, produce the methods for evaluating systems, the methods for establishing standards for these systems, rather than creating new ones. There was one other thing. When we were talking about the third year, Uwe mentioned that it was my idea to do the encapsulation, and that isn't entirely true either. One of the things that I learned when working in atomic energy facilities, that when you get a problem, you try to encapsulate it. This came from our work in atomic energy, radiation materials, that you tried to bring these things down to their smallest common denominator. And one of the problems that I began looking at in this whole business of resources conservation was to see if, in fact, we couldn't bring some of the problem down to a smaller common denominator. And so the only idea that I had was encapsulation, and the solution that won that prize here at the school was, that you saw on the left, was Bob Curtis, who's now in the fourth year. Okay, one of the things we've seen is this whole business of alternate energy sources, and one of the unfortunate things is that a lot of people are running around looking at these as though the lifestyle was going to continue. And I think we've probably come to a conclusion that it isn't. One of the things that we think that is very interesting about the AIA's position, American Institute of Architects, is that they realized, as Dan mentioned earlier, that we are not innovators of new systems, we are integrators. But beyond that, we're supposed to have some kind of an idea of the human experience in the built environment. And when looking at that, we find that there is the seeds, or the whole source, of a tremendous waste of energy. And when you put that little bit in your mind tonight, if you're looking at television and looking at all the Christmas presents, look at the profusion that are energized by electricity, and ask yourself how necessary really is it to substitute electrical energy for your arm in brushing your teeth. Well, there's a whole analysis of this then when one starts looking at encapsulation, and one of the two interesting things I did, for the heck of it, I found out what the surface area of the body was. And I compared that to the surface area of a body in a typical office. Now, the thing that sparked me was a little gimmick that Richard Petty used for several years, a secret device that blew off all of his competitors, and it was called a cool head. What it was water going by dry ice and going around the top of his head and inside of his helmet. What it was doing was cooling the hypothalamus, which is the gland within your head that establishes your temperature comfort or temperature sensitivity. So he was artificially fooling the hypothalamus, but it worked. Whereas the rest of the drivers in these 150 plus degree automobiles in a race were passing out from heat prostration, he was going across the finish line as cool as anything. So I got looking at that, that's kind of an interesting thing, and I said, what is that ratio of the skin of a human body to that office? It's 3,000 to 1. 3,000 to 1. If I can handle the thermal comfort problems at the human body, I can do it at 1/3000th that I would be doing it in a typical office. So stick that in the back of your mind somewhere. Another one was to look at the process of light. This, for example, is a good example that in physics we talk about the inverse square law. The light fails inversely to the square of the distance. If we were to move those lights, say in an office, just 7 feet from the ceiling down to the desk, we could require 1/50th the square of 7 of the energy necessary to provide the same degree of light. And we're now looking at this, we're calling it task lighting as opposed to general lighting. In our studios upstairs, we light our floors at 150-foot candles, which is considered proper lighting. But we light it at the ceiling, not at the desk, 10 feet away. We could reduce the energy requirements in that space by a factor of 100 by simply putting it down at the desk level. So these are some of the things that we've been worried about. Indiana has taken something of a lead in the United States by establishing one of the first tax advantage criterias in solar energy. And we should be very proud of that. However, there's some other factors that we have to take a look at, and these are the problems of, again, how are we building buildings, how are we building waste? And there's some precedence to this. What I'm really saying is that eventually we're going to have some laws, some codes, according to this. Well, the ones that we can look at most are the federal government ones, and we find that FHA has a long history in this in establishing U factors and certain things about houses to minimize this energy flow in housing. And we use the term prescriptive specification because they talk about specific things in this. Well, a little bit later, I would say about 5 years ago, General Service Administration began to see some of the problem and introduced something called an energy budget, in which they said that any state building could not expend more than 50,000 BTUs per square foot per year on heating, lighting, equipment, whatever. This is a typical office building. Remember, GSA owns more office buildings than anybody in the world. Well, this caused a hell of a storm, because if you take that same factor and apply it to a typical New York office building, as some that you saw that Dan was showing, you find that in fact they are using an energy on a rate of 10 times that amount. And so of course all of the engineers, mechanical engineers and electrical engineers that were working on these things said, my God, we can't possibly meet that scale. So a big brouhaha came about. And the agency, or the group of people who should really be worrying about this sort of thing, the American Society of Heating, Refrigerating, and Air Conditioning Engineers, lovingly called ASHRAE, got into the act and began looking at what does this thing really mean insofar as putting together something that legislatures could use as a part of codes. And they produced something called ASHRAE 90. And you people ought to be aware of it, because in your practice, for some period of time, you're going to have to live with it. The odds are that it will be passed as a stopgap measure, or a stop energy use measure. It is a prescriptive specification, much like the sort of thing that FHA had pioneered earlier. It does things like limiting or defining the amount of energy transmission you can have through the enclosure. It determines light levels and fixture efficiencies. It determines infiltration rates, the amount of air that comes through this door because it isn't weather stripped, and all that air has to be heated or cooled as the case may be. It talks about equipment and distribution efficiency. And it talks about energy recovery systems, because in fact we do dump an awful lot of energy. It talks about some of their own standards. We've got standards that have been passed on to us from ASHRAE about how much fresh air do we need, and a typical percentage that you'll find in most codes is about 15%. 15% of the air must be fresh air. And this whole thing is so that you get an adequate oxygen level and that you don't start asphyxiating yourself from your own effluent. We find that in fact that 15% is a bit high, that in all likelihood we could get by with numbers much less than that, much less than 5%. But with the vagaries of the kind of equipment we have, we've elected to throw the energy away to make sure that in those days we got proper ventilation in these systems. Well, one element is energy recovery. You simply, instead of dumping this energy out, as we do in a typical building in the university, all of the air that is vented out of the building, exhausted, to make up for the 15% you put in, goes out through the toilet rooms for obvious reasons. And you're dumping a lot of energy out of that. So the idea is simply put some kind of a recovery process in those exhaust stacks, take that energy and put it back in the intake of the intake air that's coming in, so that you continue to use that energy. Well, this is an excellent holding pattern. But there are a lot of people in the AIA, myself included, who feel that it is short-sighted because it is prescriptive. If you look at it hard enough, it's a hell of an inhibition to creative design or creative engineering. It does not take into advantage or into consideration some of the advantages that one can get out of interesting kinds of integration. It does not take into consideration the relationship of some energy sources that do not exist on the market. It does recognize that if you were to use non-replenishable, let me get this straight, replenishable fuels like solar energy or wood, if you do use those, you get some kind of a trade-off in the requirements of their codes. So they are looking at some of those things. But insofar as creative or innovative systems, some of which do not exist yet, it has a very definite blank wall. It's talking about off-the-shelf performance, it's talking about off-the-shelf hardware. So the AIA has taken the position that this is inhibitive and that a performance specification is far more appropriate. Now, a performance specification begins to approach the thing I was talking about earlier in energy budgets. So these are things for us to look at in the next few months and years. The state legislature, I'm sure, will be looking at the proposition of ASHRAE 90 because it does in fact exist as something that can be applied now, and legislation I suspect could appear this year out of our legislature. And I will say that it's a good holding action. Now, what does that mean? It means that something like the pyramids on 465 could never be built. It means that you're looking at something like 15% of the exterior of the building as glass maximum. It means that permissive, passive systems, as we saw in some things, are really not included. In fact, they're penalized because the glass wall that's a part of a passive system is a high energy transmitter. It doesn't recognize the fact that inside of it is a good storage element. There are some factors that I think are going to have to be worked out in that legislation to reflect these kinds of things, but I think it's going to be there. And I think in that sense it's a good one. What I am saying in closing then is that you folks, the students here at the school, have got some problems that we never heard of, horrendous technological problems in this whole business of looking at the fact that more is not better and looking at the fact that progress isn't more. It may be less. And we would sure like to have you look at those kinds of things. There's one last thing that was a part of this that I talked about at Argonne, is that we've got a lot of old buildings around us, and we find people tearing them down at a heck of a rate, and regardless of their historic value, I take great exception to that, because every single old building represents a capital investment of energy. If you tear it down, it takes energy, and to build it back up, it takes still more energy. And this is one of the things I would caution you about. Don't look at energy as a single item, as something that's going to support me or provide some light. Look also at the fact that it takes energy to make the product that goes into the building. It takes energy to transport it from the factory to its subassembly. It takes energy to transport it to the building, and it takes energy to erect it in the building, and it takes energy to move all of the people to do all of those processes. So you see some numbers that say that 30% of our energy is in the operations and maintenance of our building. Make sure you understand that. The operations and maintenance of our building. And it's far more than that to construct our buildings, to make this material, to transport it, and to transport all of the people. Because another third of our energy plus use is in transportation. So those are some big numbers. Okay, that's all I've got to say, and I'm sure there are some of you who have some questions, and the 5 of us have agreed to stay as long as you need us.